espero que hayan disfrutado del descanso. Vamos a empezar ahora con la ponencia de la doctora Raja Cherkaoui El Morsley, doctora en física nuclear por la Universidad Josep Fourier en Grenoble, Francia. Sus logros le han permitido desarrollar numerosos proyectos relacionados con la física nuclear, como la creación del primer programa de máster en física médica en Marruecos. A lo largo de su vida como física e investigadora, ha sido reconocida por su trabajo, siendo nombrada vicepresidenta de Investigación, Innovación, Cooperación y Colaboración en la Universidad Mohamed V. Entre 2014 y 2018 fue designada como evaluadora experta científica para el Centro de Investigación sobre Ciencia y Tecnología, donde actualmente es parte de la Junta Directiva. Hoy ella nos presenta su ponencia The Discovery of the Higgs boson and Ongoing Research at the Atlas Collaboration. Un aplauso.
Good morning, ladies and gentlemen, dear colleagues, dear students. I am very happy to be there and proud to be with you, and I will thanks the committee organizing committee to invite me to this very interesting, and I think you are young people, you are the future for your country. So I am you present me, I am Raja Cherkaoui, professor at the Mohammed V University in Rabat, and I am also member of the Hassan, the Academy of Science in our country, and African Academy and European Academy of Science. So today I will talk about the discovery of Higgs boson and the ongoing research at the Atlas collaboration. I am sure you all heard about Higgs boson. I will try to present you what is the Higgs boson. Here, the current understanding of our universe, the history of our universe, is based on the Big Bang theory, sometimes also called standard model of cosmology. And we can understand the history of our universe in two manners. The first one, I am trying to see. The first one is here, using through cosmologic observation by telescope, for example. You have many, many telescopes in the world. And the second is here, to go to the beginning, after the Big Bang, to create exactly the condition that less than 1 billionth of a second after the Big Bang. We are working in this case, the second case. So, particle physics. If the universe did not exist, it would have to be invited, but with what? What are the elementary particles that make up matter? This is the question that particle physics tries to answer. So you have an idea what is particle physics. The adventure began at the last century by the discovery of the first elementary particle, electron and photon. You all heard about, you know all what's electron, what's photon. It's the elementary particle. And after that, after many decades, we discover other particles. At 1960s, a model emerged that would be later called standard model of elementary particle. This model claimed to describe the universe, to explain the universe using about 30 particles. You have here the particle and antiparticle. Each particle have his antiparticle. At the creation, you have after the Big Bang. I will explain how. And here, the 30 particle, and the physicist at this area, the physicist explain particle interaction using the mathematics of field theory, which forces are carried by other particles. By particles, it's like messenger. And this particle is very important. You have it here. We call them the boson. You know one very well for force, electromagnetic force is the photon, gamma. You know it. So it's very, very important. You have the four boson here for each force. You have electromagnetic force, you have weak force, hard force, and you have not here, look, you have not gravity. So the standard model don't take up the gravity. So it is the first problem we have. And after that, all these particles have been discovered experimentally. When you have a theoretical model, if you haven't a result, experimental result, you can say it's good. So all this have been discovered. And the last one is the Higgs boson. I come here, you see the Higgs boson. The last one was being discovered at CERN, the European Organization of Nuclear Physics, at 2012. And we are member of this collaboration. And this is very important. Why? What is the Higgs boson? And why does it matter? Is the question we have always. People in the street sometimes ask me, and it's very important to show, because if you have the Higgs boson, we have not been here all. So before, it's not far from today. Before 1964, the only mathematically constant theory required boson to be massless, or it is impossible, because experimentally we find W and Z, the two boson for the weak interaction, and we found them with a large mass. So we have to change the theory. There is some problem in the beginning at this time. And to solve this problem, 3 teams of theorists proposed a solution now referred to as Broad, Engler, and Higgs mechanism. The name of the 3 theorists, physicists who present this mechanism. And this mechanism required the presence, after the Big Bang, the presence of a new field. And in this new field, through the universe, which give mass to some of the boson, and after that we understand all the particles, and we are here, and could be verified by its associated particles, the Higgs boson. How do we do that? How do we do that? The idea is very simple. We use the equivalence energy mass equivalence equation, the famous equation of Einstein, energy equal mass speed of light squared. Only that. Speed of light is a constant. That is mean why? That means that energy and mass are exactly the same thing. And in particle physics, mass is given in energy, in electron volt. It's not given like a kilogram or what you want, you know. So this is very important. If you take 2 particles and make them collide, here, for example, I have 2 protons, and make them collide with a big energy, they will disparate, you have energy. And this energy will retrieve other particles. And this particle can be a very big mass, like Higgs boson. But these particles are created for a very short time. And after that, we have decay products. And we will detect decay products, and we can have all the properties of particles before. It's the same as what we do for Higgs boson. So, how we do that? To have 2 particles. We use a very big accelerator, the Large Hadron Collider. The Large Hadron Collider, I'll show you here. Imagine 27-meter tunnel, you have, it's 27 kilometers circumference and 100 meter deep. And it's very important because the environment don't change, and this is very good. And you are far from all radiation. So to be sure to find something. And in this ring, we will collide particles at mini detectors. You have CMS, Atlas, LHCb, and ALICE. There is other little, but this is very important. So Atlas and CMS are constructed differently, but they will have the same project, Higgs boson in the beginning. So it is important to have two experiences giving the same result to be sure that we have not an error or something like that. And after that, so we will, in the beginning, we take proton. After that, we take ions. But in the beginning, we take proton and we collect them and we try to detect the decay product. And for that, we use, where I work, but you have CMS also, a huge detector, Atlas. It's not the mountain of Morocco, Atlas. It's important because in Morocco, you say, you are working in Atlas Mountain. No, it's an acronym of toroidal liquid LHC apparatus. What is Atlas? Atlas, at 46 meters long, 25 meters high and wide, and it's like an onion. You have many subdetectors. And each laboratory in the world work in one subdetector. And so you have to be careful. You have to look what the other are doing, and after what the other are doing. It's very, very important. And of course, here, for data acquisition and for data analysis, we use artificial intelligence. Now we talk about that, but before we use it, but we have not the name artificial intelligence, the difference. And here, if I take a cross-section, transversal cross-section of this detector, going from here you have, from the collision, the collision, here you have many subdetectors. And each detector will detect one particular or two particles. If I go here, the collision, point collision, you have the first, the inner tracker. The inner tracker detector measure the detection, momentum, and charge of electric charge particle. And after that, you have electromagnetic calorimeter. This is only for electron and photon. So the energy less by electron and photon. And after that, you have the hadronic calorimeter, the energy of hadron. For example, you know proton and neutron. Proton are hadron because they are made by quark. And after that, you have the muon spectrometer. Muon spectrometer is very important because he identifies muon charge if there is a muon. But muon traverse all and go on all the detector. And finally, you have the magnetic system all around in the beginning and the last. The magnetic system is how you know if you put a charge in a magnetism, the trajectory change. So we use that to have exactly the charge of each particle. To do that, it's very difficult. It's a huge detector. It's a huge electronic, huge data. So we have to have a collaboration. And the international collaboration is a worldwide collaboration, and we name them Atlas. But it's the collaboration. And it's very important. You have around 3,000 scientists in the world, from 42 countries. And Morocco joined this collaboration in the 1996, and at this time, Morocco is the only African and Arab country joining. And this only because we have two professors who decide to do that. And sometimes, in the beginning, it was very difficult. All the decision makers say they are crazy. We are a little country, we have no reach. How we can do all the things you want because we have exactly the same mind. So on July, because we know, but before, 2 years before, we understand that we have something new. But it's announced only in 2012, and the Atlas and CMS discover exactly the same thing, a new particles. In the beginning, it's difficult to say it's Higgs boson, but we have a new particles. And after that, we try to show that it is Higgs boson. Here, you see in the first and second round at two different LNG. What we are looking for Higgs who disintegrate in other particles. Here, the first one, here, is for Higgs in 4 lepton. And here is Higgs in 2 gamma. And we found exactly the same. And after that, of course, we take all the different disintegrates of Higgs to be sure that we discover the Higgs boson. Why? The first thing is Nobel Prize. It's impossible to give Nobel Prize. You can give it for 1, 2, or 3 people, not more. Or we are 3,000 physicists. So it's impossible to give them the Nobel Prize. So they give to the physicists who present the theory in 1964. So you see how many years you need to show that the theory is good or not. And in this collaboration, you need, for example, US wants to have their collider. All people want to have a rich country. It's impossible because you have women research. You have to have many physicists in this area, many engineering, so it is technician also. It's for that US and all countries, China, but now China is preparing their own collider, different, to be complementary of this. So here, there are three physicists, but only 2 who are not died at this time. So Peter Higgs and François Hegler. Peter Higgs from UK and François Hegler from Belgium. And Peter Higgs died this week, last Monday. So it is very important, it's very good, very known physicist, theoretical physicist. What's impact on science? First is the discovery, the end of a decade-long journey of research, is the first thing. And discovery, the Higgs boson, is opening other windows. Because we saw that if we discover something, we have to go ahead. No, the standard model is very good. We discover all the particles, but we have many other questions. So this model is very good, but it's not sufficient. So we have the beginning of a new chapter. The first, when we discover this particle, the question we pose, is it really the Higgs boson? And in the theory, all the characteristics of a particle, like a charge, a spin, can be calculated, but not the mass. And here we discover the mass. And the mass is unknown in the theory. So we discover the mass. So for known mass, for the Higgs, is around 125 GeV. So for a known, all their properties can be calculated. So we will measure all this property experimentally and compare with theoric. If it's the same, we are sure to have the Higgs boson. And it is important because in this experience, to have money first, to have money for Atlas collaboration, Atlas detector, to have all people, all the associated laboratory have to pay something. It's depend of their PIB and of their country. And in this, we have two sides, a real data and simulated data. So we simulated all the detector, we put them all the physics known, and we compare with real data. It's like that we discover something new. And for this, you use algorithm and intelligence, artificial intelligence. And Higgs, if you look theoretically, you have many different decay of Higgs here, many. And so first we found the mass experimentally. In the beginning, we don't know that for us, in the beginning, it will be more mass than we find 125 GeV, but it is 130 times larger than the mass of a proton. You see, so it's important. And with this mass, the Higgs boson could decay in several different ways. And if you look the research, each group look one decay, work in one decay. So you have an idea. We have around 2,000 students in the world working in Atlas, because you have many subjects. And the first thing to check was the spin of a particle, momental angular of particles. And thanks to this, we find that Higgs has zero, spin equals 0. And it's exactly what's in the theoretical model, what's proposed by the theoretical physicist. The other things we have to verify in the coupling. What is the coupling? Here, the interaction force of the Higgs boson with other particles. We call that coupling in particle physics. And here we have all theoretical calculation, and we measure experimentally. And we found exactly the same. Look here. I am not very good with that. We find exactly the same. And what we found, because theoretical model, what he say? The heavier particle, the stronger its interaction with the Higgs field. For example, gamma. Gamma has not mass. It seems that gamma don't interact with the Higgs field. He go out. He have no mass. But others, and we discover exactly the same. Look, W and Z, we have a large mass. It's exactly the field. So we discover exactly what the prediction of theoretical physics. And so we are very sure that it's the Higgs boson. But we have some enigma. First, we have not gravity. And the other enigma, what is this? It's dark matter and dark energy. What's dark? Because they don't emit gamma, so we can't see them, only that. But with cosmologic observation, we know astrophysics, we know that we have dark matter and we have energy, dark energy. So this standard model explains only 5% of the universe. Only 5%. So all the things what you are looking at is 5% of the universe. The other 25% is the dark matter. It's very important for the structure of the universe. It's this who give, because it's more than ordinary matter, 5%. The 20% is that who give the structure of all our universe. So it's very important. So we have to search to know what is this dark matter. It's very important. And we have 70% black energy. We don't see it, but it's here. We measure it with telescope. And this is very important because the dark energy is that who giving the expansion of our universe. They push our universe to expand. So it's very important. So the question we say, how can we, this collider, discover something for that? The question is simple. Before, the question we have for Higgs boson, we don't discover all the things. We are working, we have working in all data we have before. Because why? We don't, the first question, is this Higgs boson composite or elementary? Elementary it seems that it's not composite with something. The question we don't know. And other question, the Higgs boson have a mass, a very large mass. So he have to interact with itself. So we have to discover that also. This is the second question we have for this. Many people are looking at that currently in the world. We have other things. We have many other theoretical models currently. And one who are looking good is the supersymmetry model. And in the supersymmetry model, they proposed theoretically, of course, they propose many Higgs, not only one. So we are trying to have more collision to see if it is good or not. If you discover another Higgs, it seems that this model is good. So there is many people working in supersymmetry. And dark matter, of course, a dark matter has mass, is the Higgs connected to dark matter. If the Higgs have a interaction with the dark matter, it will give a decay product. And with the decay product, we can calculate, we have all the things, artificial intelligence, electronic, informatic, all the things. So we can have an idea what is this dark matter. And here you have huge people looking at that because the group will discover that it will be. And of course, we studying the property of the Higgs boson can reveal from some physics, new physics behind the standard model. We are sure that there are new physics, but we don't know why. What is this new physics? So it's the second. What are you doing? If you look, we have the Large Hadron Collider currently. I presented in the beginning. And in this Large Hadron Collider LHC, we done the run 1 with the ZTV and ATV in the center mass of proton. And after we have the run 2 for 13 TV. And now, currently, we just began the run 3. And after that, we stop. And we will update of the Large Hadron Collider by high luminosity Large Hadron Collider. What means high luminosity? High luminosity is proportional to number of collisions. So if you we are sure that in 1 year we have the collision we have in 10 years, because we will have many collisions. And many people are working in this. And the HLHC will begin around 2029, we hope. And we will have run 4 and run 5. what the future? If you update the LHC, you have to update all the detector because you will have huge data. So we have to see if we will have not problem. So the Atlas collaboration decide mini update of the detector Atlas. And this so is ongoing data, of course, currently. And after that, we will have high luminosity LHC. And the Atlas collaboration is going to upgrade the Atlas detector. And I will explain rapidly how we do that. If you like, each university in Morocco, you have a few researchers working in this area. So our ministry decided, we propose our ministry to have a network of researchers in many universities, and this network will represent Morocco at the Atlas collaboration. And we have here 1, 2, 3, 4, 6 universities currently, and an associate technical institute. It's a very, very modern institute called MAS here. And this institute, you have many things. You have not only, you have photonic, of course, very big laboratory photonic. You have electronic. So it is important to, because CERN or European organization, so see only Morocco. They don't see where is it from, or so we have to be to work together. And this is important. Here some colleagues. What Morocco done? In the beginning, we work in pre-sampler. It's in electromagnetic calorimeter. It's new. So we have to have a room we receive detectors and some component of detectors, and we have to work very hard. More than 2 years. We are all the time in the laboratory with our students, our colleagues, and we have to write all the things, because when we test, when we put our component, we send them directly to the industry. All the things in Atlas is new. It's innovative. All the things don't exist. So if you look to the patent in the world, you see that Switzerland have many patents because the CERN is there. Because all industry is looking at the innovation for this experience, because all the things. So what we do, we have a prototype. We propose for each prototype you have to have simulation by Monte Carlo, and after that, a prototype. And when it's good, you call industry to help you. And so the pre-sampler after, and now it is very important. We are in the upgrade of Atlas. And it's not easy, because for all the things, decision maker have to be there. So decision maker shows the results and say, and you have the trust of decision maker. It's very important. If you have not the trust of your decision maker, you will have nothing. See? So you have to be very careful to show what you observe. And you have always to have innovative idea. And you are young. For you, it's not difficult to have innovative idea. If you have innovative idea, you have to show what you are doing. You have the trust of the decision maker, and you have, of course, money. Without money, you have nothing. So we are, of course, and we have in data analysis. So we have to have many students. Our students work in Microsoft because there are many algorithms, many informatics. They work. Some of them work in medical physics or in industry. You can go everywhere when you pass by this very big CERN, very big laboratory. What is the first upgrade we are looking there is the high granularity timing detectors. It's a detector, we will have it in Atlas. To consolidate, we have a mini collaboration, coordinator by Spain, some laboratory from Spain. And we are in this in this, like thanks to Masir, because they have all laboratory, they have electronic designer. We are also participating in designer of this. And this is important. Why? The HGTD will upgrade Atlas from 3D detectors to 4-dimension detectors. It's very important. Why? It's to have to be sure to have the energy, the good energy, precise energy for each particle, and also to measure the number of collisions, so the luminosity. And the resolution, it will be about 30 picoseconds. So you see, it's very difficult. And the device is being developed with the active participation of Moroccan scientists, of course. What the benefit of our country? Why the thirst of our decision makers? Thanks to this collaboration, we, researchers in Morocco, not only, are a member of an important discovery in this century. All PhD students are in high level. This is very good. They can go and work in every. It's very important. If you are a student, you have a specialty, but you have to learn to adapt any situation. You have not to search only in your specialty. You learn many things, so you can work in other domain or area if you want. And with that, we have innovative training, technology transfer, of course, but we look what the other countries are doing. We have Atlas collaboration. With Atlas collaboration, we make bilateral collaboration with Spanish, with Spain, with Valencia and Barcelona, and after that, bilateral with France, with Sweden, and also with Italy. So we are looking what's happened in the world. Sometimes you say China is copied. They are right. You have to look what's happened in the world. After you can innovate it and change them. But we have to learn what's happened in the world, because the science currently is very huge. So we have the first master of medical physics in Morocco. When I proposed this master, all people say, what's this? She's crazy, always have an idea, it's impossible in our country. I do that, and all medical physics now is working in hospital, in clinic, in all Morocco. And now we have a law, like Spain, of course. If you have radiotherapy or nuclear medicine, if you have not a medical physics, radiophysicist, you can't open your clinic. Impossible, the law. So this is, we look at this time the future of our country. And after that, we have also, of course, master degree in computer science and scientific instrumentation in high energy. And currently, a new master in radio protection. New one is by one colleague. It's very important, because why radio protection? In all research we have radiation, you have to have radio protection. So this is very important. And now the International Atomic Agency call us to help them to put this master in other countries in Africa. And this is important, because you have many, you use radiation in medical, in clinic, but use also in industry, in aeronautic. So we have to learn about this. And also international award. The first, I have the L'Oréal UNESCO. We have each year 5 women in the world. They divide by Africa and Middle East, North America, South America, Europe, and Asia and Pacific. And for each area, they take 1 woman. So I have been, why? Because I innovated only. I push my country to be different, and this give award. And we have another colleagues who have Professor Humada win the ISISCO Science Prize. And I have also honored at the organization Islamic Cooperation Summit. It's very important for me because if Islamic, all Middle East, and in Middle East you have a very good women in science, very, very good. And recently, Professor Tayalati, who have Mustafa Prize from Ireland. So you see that innovative idea can give. And this is important for our decision makers, so that they say, oh, so all in the world, it's important to have money. It's like that. It's thanks to that we have in Updates Atlas, because our ministry have to give money. And what is the future of particle physics? The question is that. So we are waiting for the upcoming high luminosity Large Hadron Collider to have, it's like have a Higgs factory. So we will have a Higgs factory. We hope we discover new physics. So we are exploring what behind the standard model of elementary particles. And there is some international partner who are thinking in Europe, in US, and in China for a future circular collider with 100 kilometer circumference for the future. So they are looking for money, of course, for which country we build there, and so on. And what is the impact of high energy physics? I talk about medical physics. So you have World Wide Web is there. If you go to CERN, you see near a desk a very plaque who say here the www as discovered by doctoral students. They try and they invite, but they did not patent it. So they are not rich. And you have medical imaging, all that in CERN, medical imaging advancement, technology of environment protection and monitoring, all around the CERN you have looking at what happened in environment. And you have scientific collaboration. This scientific collaboration is new. It's like you have to be rigid. You have a convention, you've seen it. If you have we don't be good, you are ejected from the collaboration. Recently, one physicist gave a conference, and he only said man is more than woman. They are ejected because in this collaboration there is no difference between gender, between religion, between which country you are. What we want is science. So if you are talk about other things, you are rejected from the collaboration. If you look to the medical physics field, now they have a very big department in CERN about medical physics. If you look the accelerator, what means? You can have radiotherapy, you know, and production of radioisotope used in nuclear physics to therapy or to diagnostic. And for detectors, you have new development of medical. All industry are there. For medical imaging, detector, and imaging also tools. It's very important because if you have a patient, you have to have a very quick result. You can't stay a patient many hours. So some tools. And after that, you have the computing grid tools. You have grid computing. For example, with my laptop grid computing, we put all mini computer and server in the world in a grid, like electric grid. And you can, for example, with my laptop, I can put my calculation in New York when they are in the night, and I have the results a day after. And also to have a treatment plan. So in conclusion, we continue exploration. It's very important because we know that there is many things we don't understand. How is it? We have many questions. It's for that when you are in this country, we felt very, very little. You are nothing. And high energy collider remains the most powerful microscope exploring nature at the small scales. And now we are working with astrophysics because we discover sometimes we have one publication with the two. It's very important. And we have societal benefits, of course. Training for new generation, a unique model of international collaboration, and of course, technological advancement in many words. I don't speak, but you have also material. Material is very important because we discover that some material, where they are in front of radiation, their properties change. So many people are looking to that. It's very important. And thank you.
Thanks so much, Dr. Raja. We shall now begin the round of questions, if you want, or if anyone wants to ask something.
Hello. Thanks a lot for your talk. I really enjoyed it. I have two questions, if you allow me. Well, the first one isn't really a question, it's more a thank you, because it came to my mind during your presentation that the Canary Islands and Morocco have one very important thing in common, that is that we are Africans at the end of the day.
What? I don't understand.
Yeah, that at the end of the day we are both Africans, yes. And we come from less developed regions. So I think that it's really important that people like yourself show your work and are a proof that less developed regions can also do science, and we shouldn't feel lesser because of where we come from. And I think that is very important, and I thank you for your presentation, for this thought.
Thank you very much. I think because in international collaboration, don't discuss with a group or team, discuss with the ministry of our country. And after that, before I met our ministry, and I told him it's very important to learn how to talk with decision maker. The first thing I say, we have the same mind. So we are not different. They are rich, we are poor, but we can have. Amazing. The first thing. And the second, I say, if discovery, Morocco is in discovery. And the first LHC, when LHC, the Large Hadron began, of course, there is many communication around that. The communication itself said we have all the continent. And sometimes say, Africa? You have Africa? And you say, yes, we have Africa. We have Morocco. 1 week before, South Africa is here. And South Africa are rich. So they put them in Atlas and another group in CMS. So, and after that, I have some presentation in Middle East, and no, Qatar and Arab Saudi are in CMS. So nothing is impossible. Exactly. But thank you.
Thank you. And the second question was regarding the Atlas detector. You said that they are updating it to have one more dimension, like 4D. What do you mean exactly by the fourth dimension?
Yes, because before we look to the energy, the mass, and we understand the time is very important. So when I talk about 3 dimension and 4 dimension, for the fourth one is time.
Okay.
So we have to have very precise in time. So we have to change many detectors in Atlas.
Okay.
But we go only in one because it's very huge.
Okay. Thanks a lot again.
Thank you again.
Merci.
Thank you.
Well, first and foremost, thank you a lot for your speech. And I was wondering about the supersymmetry thing. I was wondering about how is supersymmetry deepening into the properties of the Higgs boson, and how, and if there's any certainty on how supersymmetry could develop the standard model. Thank you.
Yes, thank you. This supersymmetry is the model who give extension of the standard model first. And in this model, the calculation in this model show that we can have more than 3 Higgs. So if we find other Higgs, now we are going to a Higgs factory. So if in 1 year we have like all the data in 10 years, so we will be very quick. And if we discover other Higgs, we will look in supersymmetry. And now there is many models, but many physicists are sure that supersymmetry is good. But if you haven't proof experimentally, we can say that. So we are looking in the Higgs factory. We are looking if you have other new particles. If you have other new particles, we have the mass of these particles. If we have the mass, we can detect all others characteristics, and we can show what the supersymmetry purpose. If it's the same, it seems that it's good.
So there's a good chance that we could detect other particles due to the consequences of the Higgs boson, right?
We hope.
All right.
We hope.
Thank you.
Okay, thanks so much again, Raya.
Thank you.